These are the videos for additive manufacturing lecture 3. So to continue, uh, we talked about um, the different additive manufacturing techniques that you can find and the general categories of those techniques. In this current lecture, we will talk more about CAD modeling and what are some of the issues of the modeling approaches and how is it resolved in the actual build process in order to get an accurate part. Because of the way it is built, these parts are built, sometimes you are not going to get the right kind of surface finish or the accuracy that you want in or that you might be able to get in the traditional manufacturing processes like the subtractive processes such as machining. um, and because most of these processes are extremely well automated, so you have to trust the machine and the software to do your thinking process and your manufacturing process. So you are going to get some differences in how you think and how the machine is going to think. It should make it for you. So I'm going to talk a little bit about that in this class. So every product development process involving additive manufacturing machine requires the operator to go through a particular set sequence of tasks, and these are there is a lot of commonality between one machine and the other. Maybe the material will be different, the actual deposition process will be different, the processes in between will be different, but the overall set of activities are pretty much the same. And the simpler the machine, like a desktop machine, the simpler the set of task sequences. So you are not going to get as accurate a final part, uh, as you will with a very expensive type of machine. So what is important about what is interesting about a desktop type of machine? Most of the time it is low cost. In fact, our goal was to see that these machines are made and supplied at less than $99 each. But it hasn't come to that, but I think it has already come down to less than $300. So where did we start? In the early 90s, many of these machines used to cost more than $100,000 for the simplest one. You needed to spend an additional $100,000 plus for the computer controlling that machine. And the bigger machines used to cost anywhere from half a million to $1 million. Nowadays, the simplest of these machines are maybe like $500 to $1,000, maximum $5,000, and the more expensive ones are like maybe $100,000, $150,000. In the manufacturing process itself, each step is likely to have few options and require minimal effort. So if your machine is very simple and very inexpensive, then you generally have fewer choices and a limited range of materials. So you might be able to have only one type of material to play with and very few variables to experiment with. And sometimes, you have to, the software that you are using is going to be extremely simple, and it'll be difficult for you to control all the variables and so on. So the more expensive ones have a lot of um, steps and a lot of options available. The Of course, the more versatile machines are, much more difficult to operate, but they give you a wider variety of possible results. And if you are an experienced operator, if you have an experienced operator, then all these things can be put to use by those people. And they also require much more careful installation in the manufacturing environment. So in every machine typically has about 8 key steps. Some of them might be combined, but they are essentially the 8 steps. So the first one is you have to dream the part. So you have to conceptualize the part and you have to design it on your CAD modeling software. Then the CAD modeling software cannot be directly sent to a additive manufacturing machine. You have to have some kind of a translator between the CAD model and the machine. So the machine only understands two-dimensional data. Most of the time, it only understands two-dimensional data. So you have to convert that to a set of slices that the machine can easily understand, and um, you have to get that two-dimensional data that the additive manufacturing machine can understand. Then you have to manipulate that file, the two-dimensional slice data onto the additive manufacturing machine. So there will still be some things that you need to do. Say for example, if you have overhangs and undercuts and things like that, you need to go and install some kind of a support material in order that the, the part is not going to slump during the manufacturing process. Then you have to set up the machine, make sure that the machine has got enough material in storage so that it can deposit that much material. So you have to calculate, or you have to make the software, the machine understand and set up the amount of information that it needs in order to build the part. So, and then after that, it has to build the part. Then you have to remove the part from the build envelope. So the inside of that machine is called the envelope. So you know how much volume it has, so you can define the maximum size of the part that you're going to be building. Then you have to remove it, and suppose it is built with powders, there is going to be powders sticking around all over the place. Or if it is uh, some kind of a solution or a solvent or some kind of a resin, there is going to be resin. So you have to typically remove that, and sometimes these components are for show and tell, so you have to make it look really pretty. So which means you have to remove that and clean up and maybe paint it or maybe coat it with a metallic coating and things like that. So that will give you the post processing of the part, and then finally the application. So these steps are generally appropriate to all additive manufacturing technologies. There is some variation dependent on the technology being used, and in this case I'm going to be discussing most of it with respect to production of polymer parts, and but most of the steps can be generalized to metal systems as well. So what does the step 1 conceptualization and CAD modeling take? It can take many forms, from textual and narrative descriptions to sketches and representative models. So sometimes what you do is you have to, or for example, if you are building, um, I don't know how many of you have gone to a dentist recently. So if you have a root canal and a crown being put into your uh, uh, into your mouth by the dentist, what he or she does is they take the image of the location, and then it will build it on the screen, and then it will define how it is to be done and things like that. So it has to be in a form that allows a physical model to be made. And the AM technology by itself sometimes is not used to realize the final product. So there could be many stages in the development process where models can be used, so that model description is then entered into the CAD modeling software package. So these packages can be different ones, Autodesk, SolidWorks, etc., etc. And software like SolidWorks have become extremely smart in the recent days. So one of the things I would like to suggest to all of you is to go and learn SolidWorks. OSU has got free software copies. You can go in and learn the uh, SolidWorks software package. So it helps you to understand the whole design process, whole the manufacturing process, and so on. So one thing I want to point out is that additive manufacturing technology would not exist if it were not for three-dimensional CAD modeling. So, but the thing to note is that unlike other CAD CAM technologies, there is very little or no intervention between the design and manufacturing stages for additive manufacturing. So you design that and then it goes into the machine, the computer controlling that machine. There is really not any intervention between the two. So this one shows you the generic AM process. So for example, the step one is a CAD modeling. Then you convert that to a set of slices in the second step. Then you transfer that file to the machine interface. And then you have to set up the machine such that, I mean, say for example, if there are overhangs and undercuts and things like that, it will install the support material there, and then it'll tell you uh, what is the XYZ information for each of those layers, and then it will actually, I mean, then you can press go and the machine will start building the part, and then after that you remove it from the build envelope. You have to post process the material, so you have to remove all the support material and things like that. And here is a simple coffee cup. So even a coffee cup has got several steps in making it using 3D printing. So there are many different ways to create a solid model, and it could be generated by a computer user using a user interface or via reverse engineering technology. Say for example, if you have a part that um, there are no drawings. I mean, it's an old. Say for example, if you have a antique car and some of those parts are broken and there is no drawing, what do? You can take that broken part and you can reverse engineer that part and get the solid model on the computer uh, modeling software using the reverse engineering software. There could be some surface modeling components. So most of the time, these solid models are constructed by combining surfaces together or by adding thickness to a surface. So in the past, 3D CAD modeling software had difficulty creating fully enclosed solid models. Um, and what would happen is that for the casual observer, you would think, that it is solid, but it is really not. Inside is all a mesh kind of a um, part design, and it won't get completely uh, filled. And what it resulted in was, suppose you used one software, it may not always be comparable with one additive manufacturing machine. So you have to kind of play around with the software, make sure that um, what you are building is what you have designed. So this is a different interpretation of the terminology YCWIG, WYSIWIIG. What is it? What does it really stand for? What you see is what you get. So in the past, additive manufacturing machines did not always do that. So it resulted in unpredictable output from the machines depending upon the AM technology. Some of them did well, some of them did not do that well. So depending upon that, this machine companies sold a lot of machines, or they failed very quickly, very rapidly. Nowadays, the CAD software has developed to such an extent that there are very few problems with surface discontinuities, and there is extensive checking and correction software built into most systems. So when it is translating that for the particular additive manufacturing machine, or sometimes what would happen is that when you save it itself, it will ask you, are you using this for this particular additive manufacturing machine or not? And then it will check and say, hey, there are some problems here, you need to go and correct it. Or it will say, hey, do you want me to correct it for you? It will automatically do that for you. But what is to be understood is that most packages treat surfaces as construction tools that are used to act on solid models. So it has some effects on the integrity of the solid data. And now it has come to the stage where any CAD modeling software can translate their information to any additive manufacturing technology without too much difficulties. In the beginning, I mean, like, in the early 90s and things like that, if we built, I mean, sometimes we would build our own 3D printing machine with an XYZ table and things like that. And we didn't have any software. So we had to write our own G code for each of those layers. And that was real challenge. But nowadays it is not that difficult. Some of the older 3D printer models still have problems, but what happens is that um, once a CAD model has been converted to the slice data, then it automatically tells you whether there are problems or not. So the step 2 is to convert this CAD model to two-dimensional slice data. So why do we call it STL? STL means it was originally derived from stereolithography, which was the first commercial additive manufacturing technology from 3D systems. So it is just a way of describing a CAD model in terms of its geometry alone. And it removes any construction data, modeling history, etc., etc. And it approximates the surfaces of the model with a series of triangular facets. And the minimum size of these triangles can be set within most CAD software. But what happens is that the time it takes to build any of these parts is dependent on the minimum slice size and the minimum size of these triangles. So if there are so many of these triangles and so many of these slices to be used, then making this additive manufacturing model takes that much more time. So basic rule of thumb is that you have to ensure that the minimum triangle offset is smaller than the resolution of the additive manufacturing machine. And uh, what is to be noted is that nowadays um, the slice data is simply automatic. I mean, you get the CAD model and then you just incorporate that into the additive manufacturing machine interface, and it automatically generates the stereolithography or slice data. Of course, when you do that, there is a possibility that there will be errors. So you have to build the first part, and sometimes the first part is not going to work well. The material is not going to work properly, so you have to do a few trial runs for trial and errors. But what has happened is that there is a lot of software tools nowadays to detect such errors and to rectify them even before manufacturing. Manufacturing on the 3D printing machine. Nowadays, there is even software to do virtual build. It will tell you how many slices, it will tell you how much time it is going to take and how much material is required. So it will tell you, hey, um, you have only so much material in the in this machine. So this you will have to either replenish it right now, or you have to replenish it as we go along. Or it will say, if it is a spool of material, it will say this spool of material is not sufficient to build this part, so please watch out at such and such a time, and you will have to replace that spool so that we can build the part effectively. So it gives you a lot of information. I'm sorry, there is a lot of write up here, but what is to be noted is the following. You have if the slice data has some issues, sometimes the machine is not always going to tell you that. So sometimes, just to make sure, especially if your part is a functional part, so what do? You take the slice data and you have to repair it, put it through a software called Magix. And this is from a Belgian company called Materialis. And the interesting thing is that there are still not too many people who are making this kind of a software. So it will tell you that there are problems with the file generated by the CAD system, and it will prevent that. It will tell you that it will prevent the part from being built correctly. So especially with complex geometries, this is more important. So what it will do is it will create the accurate slice data. If the errors are small, then you may not even notice it until the part has been built. So you can use this software as a checking software to ensure that there are no problems with the STL data before the first part is built. So one thing that we have done is, I mean, people have done is um, they have tried to get away from STL format. Because STL is really old format and it may not give you the accuracy of the parts that you want to build. So what people have been trying to do is to create a new file format that is compatible with every single 3D printing or additive manufacturing machine there is. So in order to do that, you have to get together all the users, you have to reach consensus, and you have to get everybody to adopt it. So these are some of the steps that you want to use in order to make it in the easiest way possible. Some of the things to note in the case of the stereolithography slice data is that um, the corresponding triangles in the files must all be pointing in the right direction, because this will control the direction in which the material is going to be deposited or laid down on that particular layer. So, which means that there has to be a normal vector associated within the triangle, and whether that the which side of the triangle is outside versus inside the part. So that will tell you how the layer of material is going to be laid down. You may not understand what I'm talking about here, so I would advise you to please go in and um, Google these things and find out what exactly I'm talking about. Okay, so the goal is that if the part, I mean, if the material is not laid down properly, you are going to have gaps in the surface. So, which means that you have to go in and correct the STL data such that there are no gaps. But sometimes some of these machines will process the STL data in such a way that the gaps are bridged, but um, in some cases you may not have proper material put in there, or you don't want unwanted material to be put in there, which will make it hard for you to lay down that layer. So if your layer is not flat or layer is not the right size and shape, then you are going to have issues. So nowadays what is happening is that you have new formats being used. So that's called additive manufacturing format. So the CAD model will ask you what kind of format you want to save this data in, whether it is STL format or whether it is in AMF format, etc. So it will, depending upon that, the information is stored differently. So nowadays, what is happening is that um, it is depositing this material, or storing this material in a meta format. So the machine can, what is happening is that it will create a text based data. So what is the advantage of this? Size of the file. So nowadays, the the size of this file is so small, so it is much easier for you to transfer this data um, online and things like that. So you make the data and then you transfer it to somebody who is building it for you and things like that. So it makes it easier for them. So this is XML data. How it is done was originally designed by folks from Cornell, but it is, and it is being used by several people, including folks at Materialise. So the general concept is that, so this is a generic format of how this data is prepared and stored, unlike the standard STL format that used to be used for the past 20 plus years. So here what they do is that every part is defined by volumes and materials, and the volumes are defined by the triangular mesh and the materials are defined by properties and names. and you can specify the color properties by color or texture, and you can combine the materials. So you can have multiple materials being laid down one after the other, or you can blend them and you can deposit them and things like that. And then once you do that, you can repeat that to get the right kind of packing and orientation of these materials into the component that you want to build. For example, this is the standard format. So this is the CAD model itself. See, additive manufacturing format. And so this is how the slice data will look like. So the whole component, this is all the size of this file. So you do not have to have every single layer to be specified in your file. So it makes it easier. So in the earlier days, you can see that the standard STL files, which were storing this file in ASCII data. So it was around, I mean, suppose, for example, this is a simple thing, chess piece, okay? So the size of this file in ASCII data, ASCII STL, is about 800 kilobytes. If it were binary STL, then it is 200 kilobytes. Then it is additive manufacturing format, then it is 300 kilobytes. But if you are making them compressed, or a zip file, you can see that it is about 25 kilobytes. So I mean, this is for such a simple part. Suppose you are building a whole um, car or a whole um, automobile by 3D printing. Just imagine the size of this file, and if it has to be transferred from one place to another, it makes it easier if you have it in this format. And depending upon the number of triangles, okay, see the size. So the binary STL file, if you have this many triangles, it is 49.6 megabytes. So it's not going to be easy for you to transfer these files from one location to another. But suppose it is in AMF compressed form, it is about 12 megabytes. So it's much easier to